Hello, I'm Mike Roberts, and I'm going to talk about Hypersim, which is a new synthetic dataset for indoor scene understanding. And it's also Apple's first large public image dataset for AI research. Okay, let's start with something we can all agree on. Collecting per pixel annotations for real images is hard. In response to this challenge, the computer vision community is increasingly relying on synthetic data, which provides per pixel annotations automatically. But if we look at the landscape of existing synthetic datasets, we see that they're missing important ground truth modalities. For some datasets, the underlying 3D assets are not publicly available. Others are missing semantic segmentation information, and others are missing an intrinsic image decomposition, where each image is factored into disentangled lighting and shading components. So our goal in this work was to build a new synthetic dataset with richer ground truth to support more holistic scene understanding. And here's what we came up with. We built a dataset called Hypersim, which includes 461 distinct indoor scenes and 77,000 high dynamic range images. We built it entirely from publicly available 3D assets, and all of our image data, as well as all the code we used to generate our dataset, is available online from our GitHub. Hypersim is the first dataset to provide direct supervision for 3D mesh reconstruction, semantic segmentation, and inverse rendering tasks. For each image in Hypersim, you get pixel-perfect depths and surface normals, instance-level semantic segmentation information, and an intrinsic image decomposition. In addition, complete 3D scene geometry and camera information is available for every scene and every image. I'd also like to mention some really exciting concurrent work. There is a similar dataset called Open Rooms by Lee et al. That was just released a few weeks ago. It contains similar ground truth to ours and is absolutely worth checking out. We evaluated the sim-to-real transfer performance of our dataset on a semantic segmentation task and a 3D shape prediction task. For both tasks, our methodology is to pre-train on Hypersim, fine-tune on an appropriate real-world dataset, and evaluate performance on the real-world dataset. We found that pre-training on Hypersim reduces the need for real-world data by 75% for 13-class semantic segmentation on the NYU v2 dataset. In other words, pre-training on Hypersim and then fine-tuning on 25% of the real-world data is better than no pre-training, but training with 100% of the real data. For 40-class segmentation, we found that Hypersim reduces the need for real-world data by 50%. We compare these results to existing datasets in more detail in our paper. We also found that pre-training on Hypersim achieves state-of-the-art performance on our 3D shape prediction task. For this result, we're evaluating on the S2 Pix3D test set, which is the most challenging test set in Pix3D. So what are the main takeaways here? We built a new dataset that's well suited for geometric learning problems that need direct 3D supervision, multitask learning problems that need to reason jointly over multiple input and output modalities, and inverse rendering problems. We found that our dataset reduces the need for real data on real-world scene understanding tasks and achieves state-of-the-art performance on Pix3D 3D shape prediction. It's easy to generate your own custom synthetic datasets using our code in case you want more control. And finally, all of our data and code is publicly available online, which is an exciting step for Apple. Thank you.